Welcome online lecture series in wireless mobile communication. Before we start the HATA model, now we have seen some drawback of the previous models. Now, the drawback of your OKUMURA model is wholly based on the measured data. So there is no analytical explanation from which this data has been taken. So in certain cases, it causes can be extrapolated. Before we are going to in HATA model, we know that in some cases this is in earlier days a OKUMURA model were based on the empirical studies. So OKUMURA did comprehensive measurements in 1968 and came up with a model, discovered that a good model for path loss was a simple power law where the exponent n is the function of frequency, antenna height and etc. One of the most widely used model for signal prediction in urban areas. It is applicable to frequency range 150 megahertz to 1920 megahertz and can be extrapolated up to 3 gigahertz. The distance is 1 kilometer to 100 kilometers. So why this model is failed in rural area? So the HATA and extended HATA model is the empirical formulation of the graphical path loss model and provided by the OKUMURA and is valid from 150 megahertz to the 1.5 gigahertz, 150 gigahertz. So in certain assumptions, it is up to 150 megahertz to the 2 gigahertz, 1.5 gigahertz. So general concept was MATA is, we already know, empirical formula for the propagation loss derived from a OKUMURA model, and it is facilitate to automatic calculations. The propagation loss in urban area is presented in a simple general format A plus B multiplied by log R, where the A and B are the function of frequency and antenna height, and R is the distance between the base station and the mobile station. It is also known as the separation distance. The model is applicable to frequency up to 100 megahertz to 150 megahertz. Distances which is covered 1 kilometer to 20 kilometer, base station antenna height 30 meter to 200 meters, and mobile station antenna height is 1 meter to 10 meters. The model is simplified due to the following limitations: isotropic antennas, quasi smooth, it is not regular drain. The urban area propagation loss is presented as the standard formula. Correction equation are used for the other areas. Although the HATA model does not imply path-specific corrections, so it has significant practical value and provide prediction which are very closely comparable with the OKUMURA models. So what are the OKUMURA models pros and cons? OKUMURA model is wholly based on the measured data and does not provide any analytical explanations. And for many situations, extrapolated of the derived curves can be made to obtain the value outside the measurements range. The validity of the such extrapolation depends on the circumstances and the smoothness of your curve in the questions. The major disadvantage is its slow response to rapid change in terrain. The model is fairly good in urban and suburban areas, but not as good in the rural areas. The common standard deviation between the predicted and the measured path loss values are around 10 dB to the 40 dB. Another pros and cons is it is derived as a numerical fit to the curves published by the OKUMURA, such as the model is somewhat specific to Japan's propagation environment. It assumes that there is no dominant obstacles. So the between the transmitter and the receiver, it is only falling on the line of sights, and that the drain profile changes only slowly. So the measurement has shown several advantages to the approach for effective antenna height calculations. So circumvent the problem, some predictions tools examining the alternative methods for calculation of the effective antenna heights. The parameter range does not encompass the 1800 megahertz. This is the frequency range most commonly used for 2G and the 3G cellular systems. And this was solved by the COS 231 HATA model. So HATA model is the empirical model of the graphical path loss data from the OKUMURA, and it predicts the mean path loss for different channels. It is valid for UHF and VHF, very high frequency and ultra high frequency band. And under this, it covering the range 150 megahertz to 1.5 gigahertz. 150 megahertz to 1.5 gigahertz is only valid under the ultra high frequency and very high frequency band. So we restrict to develop the antenna only in this band only, and that antenna is used for UHF and VHF transmission and receptions. So the chart used to categorize factor affecting mobile land propagations and standard formulas for approximating this urban propagations loss. So we need a correction. So we need include this correction under the sum situation. So the correction factor for the sum situation and compares closely with the OKUMURA model as D should be greater than 1 kilometer. The separation distance between transmitter and receiver should be greater than 1 kilometer. Then it is used in the large mobile systems. It incorporates the graphical information from a OKUMURA model and develop it further to realize the effect of diffraction, reflection, and the scattering caused by these structures obstacles. So OKUMURA HATA model, if simply we have combined these two models, you can say simply it represents the curve fitting of the OKUMURA original results. So it is applicable for transmit antenna effective height 30 meter to the 200 meter, and mobile antenna height is 1 meter to the 10 meters. So the what is the transmit antenna effective height is 30 meter to the 200 meter, and Mobile base station, mobile antenna height is around 1 meter to the 10 meters. And frequency range is used 150 megahertz to 150 megahertz to 1500 megahertz. Yeah, in simple word, it is 1.5 gigahertz. So sometimes it is written as 1115 megahertz. It is means it is the 1.5 gigahertz. So the transmission distance between transmitter and receiver, that is donated by small d, and it is nothing but 1 kilometer to the 20 kilometer. And that implementation, the path loss can be written as PLA plus B log D plus C. It is calculated in dV, where A, B, and C are factors that depend on frequency and antenna height. So A having the equation A is equal to 69.55 plus 26.16 log cutoff frequency minus 13.82 log of HB and minus AH of M. And the B is having the equation values 44.9 minus 6.55 log H of B. And where FC, and the cutoff frequency given in the megahertz, and D is calculated in kilometer. So this equations normally written as L50 calculated power loss in dV is equal to equal to 69.55 plus 26.16 log of FC calculated in megahertz minus 13.82 log of H of TE minus A of H of RE plus 44.9 minus 6.55 log of H of TE of the log D. This is our main equation. This is our main HATA model equation. Whereas we are not having any derivation for this, to remember this big huge equation for finding the path loss in a HATA model. So where where f of c is the frequency in megahertz from 150 megahertz to 1500 megahertz, and h of t is effective antenna transmitter transmitter that is also known as in wireless mobile communication base station antenna height. Antenna height measured in meters, which is ranging from 30 meter to 200 to 200 meter. The effect H of RE is effective receiver mobile station antenna height which is in meters and it ranges ranging from 1 meter to the 10 meter. 1 meter to 10 meter. Small d is the separation distance between transmitter and receiver, that is TR, separation distance, which is calculated in kilometer. Separation distance in kilometer. A of HE HRE 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 correction factor for for effective mobile antenna mobile antenna height, which is a function of the size of the coverage average area for a small to medium 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 size city, the mobile antenna correction, the mobile antenna correction. So the value of h of re is 1.1 log fc minus 0.7 bracket close multiplied by h of re minus 1.56 log fc log of fc minus 0.8 bracket close dV. This is the medium size city. Medium size city. Now we're going to write a very important formula, that is the A of H of RE is equal to 8.29 log of 1.54 H of RE का whole square minus 1.1 dV for the FC is less than equal to 300 megahertz. The second value is A H of R E is equal to 3.2 ब्रैकेट में log 11.75 H of RE का होल स्क्वायर माइनस 4.97 dV for FC is greater than equal to 300 megahertz. This is the second. This equation play a very important role. And it is the large size city. So L50 dV is equal to L50 urban minus 2 of log of FC divided by 28 का ब्रैकेट का होल स्क्वायर माइनस 5.4. This is the part loss in suburban area. बस दो मिनट L50 dV but dV is equal to L50 urban minus 4.78 log FC का होल स्क्वायर माइनस 18.33 log of FC minus 40.98 open area. So final equation is L50 dV is 69.55. This is the final equations. L50 R1 dV 69.55 26.16 log C minus 13.82 log H of T minus log H of RE 49.9.6.55 log of HT log.